What if I told you that a spinning pile of rubble hurtling through space could hold the key to understanding where Earth's oceans came from? Welcome to the extraordinary story of asteroid Bennu and its water-soaked secrets. When NASA's OSIRIS-REx spacecraft arrived at asteroid Bennu in December 2018, scientists weren't just looking at another space rock. They were staring at a cosmic time capsule that's been preserving water molecules for over 4.5 billion years. From the very first observations, instruments detected something remarkable across Bennu's entire surface: the unmistakable signature of hydrogen and oxygen atoms bonded together in clay minerals. This wasn't liquid water sloshing around, but rather water molecules locked inside the asteroid's rock structure. Let's break down what surface hydration actually means. Imagine a sponge that absorbed water billions of years ago and then got freeze-dried in the vacuum of space. The water molecules didn't disappear. They became chemically bound within the mineral structure itself. On Bennu, these hydrated minerals appear as phyllosilicates, which are clay-like materials that form only in the presence of water. These aren't just traces either. Spectroscopic data revealed that hydroxyl groups, which are hydrogen and oxygen atoms bonded together, are distributed across Bennu's entire surface. The discovery came from analyzing how sunlight reflects off Bennu's surface. Different minerals absorb and reflect light at specific wavelengths, creating unique fingerprints that scientists can read. When OSIRIS-REx's instruments scanned Bennu, they detected absorption features around 2.7 micrometers, a telltale sign of hydroxyl-bearing minerals. This signature appeared everywhere the spacecraft looked, making Bennu one of the most hydrated objects ever studied up close. Bennu itself is a peculiar character in our solar system story. This asteroid measures about 490 meters across, roughly the height of the Empire State Building. But here's where it gets weird. Bennu isn't a solid rock. It's what scientists call a rubble pile asteroid, meaning it's essentially a loose collection of boulders, rocks, and dust held together by gravity. Think of it as a cosmic beanbag, with material ranging from house-sized boulders down to fine particles. The asteroid completes one rotation every 4 hours, which is fast enough to create a slightly flattened shape at its poles. Bennu's surface temperature swings wildly, from about 73 degrees Celsius in sunlight to minus 73 degrees Celsius in shadow. Despite these extremes, those water-bearing minerals have survived, protected within the rock matrix for eons. What makes Bennu's hydration story even more fascinating is where this asteroid came from. Scientists believe Bennu originated from a much larger parent body in the asteroid belt between Mars and Jupiter, somewhere between 700 million and 2 billion years ago. A catastrophic collision shattered that parent body. Bennu formed from the fragments, inheriting the hydrated minerals that had formed deep within the original asteroid. When liquid water flowed through its interior, the parent body itself formed during the solar system's earliest days, when our cosmic neighborhood was a chaotic nursery of colliding planetesimals. Water was abundant in the outer regions, where temperatures were cool enough for ice to exist. As these icy bodies collided and merged, water infiltrated the rocky material, creating the hydrated minerals we see on Bennu today. Here's where the story connects to Earth. Our planet's surface is covered by oceans, but scientists have long debated where all that water came from. Earth formed in the inner solar system, where temperatures were too high for water ice to survive. The leading theory suggests that water arrived later, delivered by asteroids and comets that bombarded our young planet. Bennu represents exactly the type of asteroid that could have played delivery service billions of years ago. The OSIRIS-REx mission didn't just observe Bennu from a distance. In October 2020, the spacecraft performed a daring maneuver called touch and go, or TAG, where it briefly touched Bennu's surface to collect a sample. The spacecraft's sampling arm sank about half a meter into the surface, revealing just how loosely packed Bennu's material really is. If you stepped onto Bennu, you wouldn't stand on solid ground, you'd sink right in. The spacecraft successfully collected about 250 grams of material. And here's the exciting part. That sample returned to Earth in September 2023. Scientists are now analyzing actual pieces of Bennu in laboratories, studying the hydrated minerals in unprecedented detail. Early analysis has already confirmed the presence of water-bearing clay minerals and even detected carbon-bearing compounds, the building blocks of life. The implications extend beyond just understanding water delivery. Hydrated minerals on asteroids like Bennu could serve as water resources for future space exploration. Astronauts traveling through the solar system could theoretically extract water from asteroids for drinking, breathing, or even rocket fuel. It's like finding gas stations scattered throughout space. Bennu's hydration also tells us about conditions in the early solar system. The minerals formed at relatively low temperatures, probably below 100 degrees Celsius, suggesting that liquid water persisted in asteroids for extended periods. This environment could have been conducive to complex chemistry, possibly even the formation of organic molecules that eventually contributed to life on Earth. Researchers have also discovered that Bennu is still active today. The spacecraft observed particles being ejected from the surface, possibly caused by meteorite impacts or thermal stress as the asteroid rotates between sunlight and shadow. Some of these particles might be water molecules being released. As minerals break down under space weathering, the asteroid's orbit brings it relatively close to Earth every 6 years, which is why it was accessible for the OSIRIS-REx mission. But this proximity also makes Bennu potentially hazardous. There's a small chance, about 1 in 2,700, that Bennu could impact Earth in the late 22nd century. Understanding its composition, including its hydration, helps scientists model what would happen in such an event. Bennu isn't alone in harboring water. Scientists suspect that many carbonaceous asteroids contain similar hydrated minerals. These asteroids represent a significant reservoir of water in our solar system, perhaps containing more water in total than all of Earth's oceans. It's scattered across millions of space rocks, locked in mineral structures, waiting to tell us more about our cosmic origins. The ongoing analysis of Bennu's returned sample continues to reveal surprises. Scientists are finding minerals that only form in the presence of water, organic compounds that could be precursors to life, and isotopic signatures that help trace the asteroid's history. Each discovery adds another piece to the puzzle of how our solar system evolved and how Earth became the water-rich, life-bearing world we call home. So the next time you take a sip of water, remember that it might have arrived on an asteroid much like Bennu, carrying ancient hydration across millions of kilometers of space. What other secrets might these cosmic travelers be hiding in their water-soaked rocks?